I didn't have to prepare today because I noticed that a lot of students took concrete with me. So once you pass it, you should be able to explain to Max how to do slab.
I charge a lot of money for instruction, Andy.
Ready to pay? Bring your check.
I can't work for free.
Want to try? Kevin, right? Kevin Torres.
Yeah.
Kevin Torres. What's your name? Chris? Chris. Ah, lucky. Chris said, don't remember my name. Hey, Mohammed.
Yes, sir.
How to design slab?
Fourth order
First, you have
differential
to figure
equation.
out the length and the width of the slab.
Okay, all right. Okay, I'll draw it up. That two-story building, what's the dimension? What's the dimension of that two-story building? 40/90? I have a lousy drawing. It's not to scale. Okay. Assume that this is 20. And assume that this is 30. Okay? Even though it looks just about the same. Okay? So if we went to the architect and show him to give us 2 more columns, okay? Then we connect all the columns together. We have a 3-span continuous beam in the long direction, 2-span continuous beam in the short direction. If this is our structural floor plan, we end up with 6 two-way slab, okay, 6 two-way slab, and 9 and 8, 17 beam, or 4 2-span beam and 3 3-span beam, okay? So if I label this, I will have B1, B1, 9-4. Look, man. Really? Hey, check. They want to check the latest market price for a kilo. How much? Okay, let's change this. What's the latest price for the gasoline? How much a barrel?
It's 20-something, 29. Low, it's low 30s.
Below 30?
Yeah, below 30 like 2 days ago, or on Thursday.
He said it's cheaper than a regular fried chicken.
Really?
Yeah.
You're talking about a barrel, right? Or are you talking about a gallon of gas?
A barrel.
Yeah, it's low 30s right now.
Is it time to buy?
No. Wait till the big boys buy.
Oh, really?
I do.
Okay, guys. Notice the way I label it, B1, B1, B1. It's actually 1 beam with 3 span. A continuous beam with 3 span. Okay? B1, B1, B1. Okay? And probably B2, B2, B2. Why? If I split the top half of the slab to be carried by that beam, the bottom half of the slab carried by this beam, the bottom beam and the top beam carry the same thing, symmetrical. But the one in the middle carry double of that. Top half, bottom half, right? So this is supposed to be bigger than this, okay? And many of you are very genius, okay, to cut costs. So you say that, hey, maybe in that case I decided to be 2, okay? And I'm going to use B1, B1 on top, one at the bottom. B2 also, okay? In that case, it is just one floor, no big deal, okay? But if you have 100 floor look like this, then you're going to have to call up Mr. Trump for him to pay for it because he's rich, okay? Mac couldn't afford it, okay? Okay, now then repeat this. This beam and this beam will be B3, 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 B2. And with same explanation, this will be B4, B4, B4. Okay? All this slab, S1, 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 S2, S2. Okay? And each of this, S1, S2, are two-way slab that you guys don't know how to do it yet. Okay? But who knows? You guys may have self-study skill, read advanced reinforced concrete, and decide two-way slab. You can decide like that. But will most of you know one-way slab? Just now, with the knowledge of two-way slab, we proceed to decide a slab, right? But you don't. No one-way slab has a requirement that the ratio of the long versus the short has to be 3. Okay? You follow the book, it said 2. If you follow Métis, I don't design one-way slab with a span ratio long versus short equal to 2. Unless it's 3, then I don't feel comfortable that it will be one-way distribution. So if the longer direction over the short is 3 times, I'll decide as one-way slab. Okay? So in this case, it's 20, 20, 30, 30, 30. I'm going to run secondary member across this. Oh. Okay. Each of my slab, each of this now has a dimension of what? 10 by 30? Is that right? So with a 10 by 30, a slab of 10 by 30 is one-way slab. Okay? One-way slab means it's supported by the beam on both sides of the long direction. If you cut your slab into the shape of this table, you load it, most of them support by this beam and that beam. Very little that go to these two end beams. And the logic is you cut a 45-degree angle, we call yield line, okay? So you create a trapezoidal, and all the trapezoidal go into the long direction. The little triangle at the end go to this beam. So the longer the strip, you can actually split it in half, and everything go to the left and the right, okay? And that's what is called one way. The load only acts in the short direction, supporting here and supporting there. Okay, clear? So in this case, notice 1, 2, 3, 4. You have 4 continuous slabs. in the short direction. Make sense? Okay? So if I cut a 1 foot strip, cut a 1 foot strip, 12 inches, okay? That 1 foot will be supported here, 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 and here. Okay? And that will be a 1 foot width slab. It's like putting these 4 tables together. And each of the joint that it forms is the support. So you have 4 continuous slabs connect into one piece. Whether it's near this edge, in the middle, or near the right edge, we have the same thing. Okay? So if you take that out, you're going to get a structure look like this. Okay. Top beam. First. Second. Third. 3. 4 span, right? Okay? And each of them 20 feet. 10 feet. Okay? And this is the beam. It represents this beam, those 5. Okay? And what is the width of this? 12 inches. Okay? That's your slab. Because we cut a strip of the slab. Okay? Make sense? And this strip that we analyze is here, 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 here. Any one of them. Any strip behave the same thing. Okay? Now, on top of that, let's say you put uniform load on it. Okay? Now, let's say the floor you're using 40 pounds per square foot ESF. Okay? Office? Is that right, office? Okay. You have 1 foot width, 40 PSF multiplied 1 foot, 40 pounds per linear foot. Okay, so you have a uniform load. On top of this, 40 pounds per linear foot, which is your omega distributed load. 4 span. Okay? Muhammad?
Yeah.
5 moment diagram of 4 span. You're going to have to put hinge and cut more section.
Yeah.
Where are you going to put the hinge? To cut the section.
There's no hinge in there, though.
No?
He said there's no hinge.
If you have hinge, I'm not going into your slab or the building or the floor that you design. Okay? The slab is this.
Yeah.
Right? We are sitting on a piece of slab. If you have a hinge in the middle, I'm not coming in. It's not stable.
So then what are those connections in the parking deck that let the parking deck move?
Oh, that's expansion joint. Expansion joint is nothing like 2 buildings just built next to each other because it's getting too long. Okay, and they were concerned that temperature or thermal expansion that might twist your building. So they cut it and leave room for thermal expansion. Let the steel member breathe. Okay, when it's hot, it expands. Okay,
So how do they take thermal expansion into account?
what is the thermal equation? Thermal expansion equation.
Thermodynamics, so.
What?
We didn't take thermodynamics.
No, it's in your strain materials.
Oh, yeah.
Coefficient of thermal expansion. What's the
Alpha.
equation?
Something with an alpha.
Yeah.
Alpha T
Yeah,
Times
alpha
stress.
is coefficient of thermal expansion.
stress alpha T? I don't know.
Yeah, alpha T is right. Right? You don't understand alpha, right? That she was talking about. What is called? What do we call alpha? Coefficient of thermal expansion. Right? For steel, it have a number. For aluminum, it has another number, something like that. Okay? You remember what is the unit of alpha? Something per degree. No, it's actually this. Okay, I'll take 1 minute to explain that. I don't know, I don't remember the equation, but I only remember what you said. The coefficient of thermal expansion has a dimension of strain per degree expansion or shortening. If you heat it up 1 degree, you cool it down 1 degree, it's going to give you that strain. That's the unit of the coefficient of thermal expansion. But what we are interested in is, if we have a beam of 10 feet made up of steel, right? And you heat up 50 degrees, how much is going to expand? Okay? So, per degree, right? So, heat up 50 degrees. Heat up 50 degrees.
Times E.
Alright? Per degree, so if we multiply heat up 50 degrees, we get strain. What is strain? Elongation divided by initial length. Alright?
It's E.
Elongation, initial length. So your expansion alpha delta T L, coming from the definition of the strain. All you have to do is remember the unit of your coefficient of thermal expansion. Easy? So don't learn it by equation, right, Chris? We talked about this morning. Learn it by understanding. So what that means, if I have a 10 feet, go up 50 degree, this material property, right? Then I can calculate it's going to stretch for half an inch. Okay? So I'm going to need to leave the gap half an inch. If you leave the gap half an inch in your building, what comes with it?
No building.
It's going to leak all over the place, right? You'll leave the gap right on top of your bedroom, on your bed. So when it rains, turn your bed into a water bed. So when you solve the problem, you ground it. So if you walk around a long building, okay, I think the easiest way to look at it is the walkway that connects between Fenster Hall and Student Center. Look at the two joints. Okay, when the walkway go into Fenster Hall and the walkway go into Student Center, it definitely has a rubber joint. Okay, good? And most of the building has it. We call expansion joint. So as the parking deck, right in the middle of the span, the span, you will see there's a rubber strip. If you park by that area, it's bouncing up and down much more than others. Usually don't park there. Okay? So what's the best place to park there? The safest place.
On the street.
Good answer.
By the elevator shaft.
In
Tune-in teacher lot.
in the deck. If you have to park up there, have no choice. Where do you park?
Next to elevator.
You're right. Closest to the gong, near the elevator. That's the strongest part of the building. Okay? Somewhere right in the middle, stay away from it. Especially at this expansion. Okay, so we have a slab, but we cut it down into 4-span continuous beam, okay, with a width of 12 inches. So what should be the thickness? If you go to your steel textbook, they will give you, refer to, first guess, use table 9.5a of ACI code, which will be L over 18 or 20. And your slab will come out about 8 inches or 10 inches. Okay? That's for post-tension pre-stress, not normal reinforcement. Okay? If you use about 4 inches, it should be more than enough for your project. Okay? So, if you guess the depth of your slab equal to 4 inches. Okay? Those are typical slab thickness in normal building. Okay? This is your slab. Total thickness, H equal to 4 inches. You're going to need cover, right? So your rebar is at the bottom. So you can have cover. Bar diameter. Okay? The centroid of the bar to the top will be your D. So your effective depth will be the total height minus cover minus half the diameter of the bar that you want to use. That will be your effective depth. So if you decide to use number 4 bar, what's the diameter of number 4 bar? Good, half an inch. So half an inch divided by 2¼ inch, right? Your cover for slab is about 3/4 of an inch. So 4 minus 0.25 minus 3/4 minus an inch. So your effective depth equal to 3. You know your effective depth equal to 3. You know your B equal to 12. Okay? It's act like a B. Your BB squared. Right? Now the next thing is, hey, all of this. What's your moment? Keith, what's your moment? The moment looks something like this. Negative, 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 negative. Whoop, 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 whoop. Okay? Yeah, Keith. What's the moment? In your steel Bible, it gives you the maximum of, I think, 3 span. Right? Chris, would you take a look at the end of the beam? It's right before the column. Okay, toward the end of those charts. 3 dash 230.
230. What do you want me to look for?
Whether they have 3 or 4 span. Yeah.
No, they have.
Oh, they do have 4 span.
Yeah.
Oh, good. Okay. You can actually, if you have 4 span, you can just get all the moment coefficient of this. Okay? Guys, most of you will decide putting the load fully loaded over all 4 span, right? But the truth is, sometimes it's not true. Okay? Last week, I walked over here before we went to the class. This room was empty. So basically, if the first span represents this room, 0 load. See what I mean? So in actual design, you're going to have to analyze this. Draw the moment diagram up, all 4 span fully loaded. Then skip the first span, load 3. Skip the first 2, load the next 2. Okay? Load the first and the third, skip the second and the fourth. You're going to have to look at some of these load combinations. Okay? And look at moment at, we only worry about maximum negative moment above the support. Maximum positive moment right at midspan of each span. Once you have that, you can stick the negative steel and the positive steel based on the chart that I just gave you. Okay? That's one way to do it. You dump the load into the computer will give you this. Okay? But again, as I said, most of you will probably go with fully loaded, which is not the worst scenario. Okay? Okay. Why I said that we have 4 span and fully loaded it is not the worst scenario. When we load this span, that span popped down, right? Is that correct? And then what happened? It kicked the adjacent span up. See? So if you load this span, it's counterbalanced. But if you load one, skip one, you load this one, this pop down, that pop up, right? If I load this one, it's already popped down due to this. You push it further. So load one, skip one, load the next. That will give you the worst moment scenario. Then loaded every span. But all this, where did you pick up all this, Mohammed?
I'm sorry.
Were you with me?
Yeah. I didn't really hear the question.
Just you? Your mind is not?
Wait, what?
You have a girlfriend?
No.
Or you go with domestic partner?
I'll just get back to Matthew.
Okay, guys. When you come across multiple span beats, and you really want to analyze the worst situation of maximum positive, maximum negative moment, we do have to play with different load possibility on different spans. Okay? And all the design, our design must be able to cover every possible load combination that can happen. Okay? Now, notice what is the chain that one span is loaded, the next span is skipped, and then the third span is loaded. Why not? There's a class in this room, skip that, the third class has still load here, skip one, load another one. See that? Okay? Those are some of the situations that happen. Okay? So, in any case, that's from structural analysis. But a shortcut is to use ACI moment coefficient. Remember that? Dominic?
You gave us the,
Okay. So, what is ACI moment coefficient? The largest is first interior support, minus 1 over 10. Minus 1 over 10. This one, minus 1 over 11. Okay? Well, I'm going to skip this first for the time being. This one is plus 14, plus 1 over 16, plus 1 over 16, plus 1 over 14. Now, at the end, there can be 3 possibilities. If it's a roller, which usually we don't have it, it will be 0. If it's a column, if it's a beam, okay, if it's a beam, minus 1 over 24. If it's a column, minus 1 over 16. Okay, for the in negative moment, it can have these 3 numbers. But most of the time in real building, we deal with either supported by a column at the end or supported by a beam at the end. For the slab, it tends to be supported by a beam at the end, which the negative moment will be minus 1 over 24. So now if you know your omega, you know your span length, with all the coefficients, you know moment, negative, positive moment at all these critical locations. Okay? With that moment, with that B equal to 12, with the depth, the effective depth equal to 3, you should be able to find AS. Okay, clear? Theoretically, you use the largest moment minus 1 over 10 omega L squared to calculate whether that depth is enough and find the AS for that depth. Once you have that, you're not going to change the stack near that end. One thickness, right here, another thickness. Okay? Whoever designed that, good luck when you build it. Okay? So you're going to keep the same slab thickness across. And when you go into 1 over 14, 1 over 16, all you have to do is, using the same BD, change the moment. With a lower moment, you get a lower AS unit. With that same BD. Okay? So with the moment, you get your AS. You don't go into say, hey, use to number 6 bar, something like that. You are calculating still require per 1 foot width of the slab. Okay? That's when this first table comes in. If, let's say from the calculation, you need about 0.2. If you need about AS equal to 0.2 square inch per 1 foot width of slab. So what do you use? If you use number 3 bar, the top number is area of steel per 1 foot width. Okay? The bottom number is per meter. So just use the top number in each of these slots. So if AS requires 0.2 square inch per 1 foot width, and you use number 3 bar, so what should be the spacing? Run it down. Number 3, the left side is the spacing. Number 3 at 6 inches will give you 0.22 square inch per 1 foot, which is more than what you need. And that's what you need. If you say that, oh no, I don't want to use number 3 bar, I want to use number 4 bar, and you need 0.2. So number 4 bar with what spacing will give you 0.2? 12 inches. Number 4 bar at 12 inches will give you 0.2 square inch. See that? So that's how this table, we make use of this table to specify how we reinforce the slab. And once you have that, it just reinforce the top and bottom based on this. Okay? The one on the top, one way solid slab. Okay? Slab done. Easy? Yeah.
I get what slabs are for short building, but what if you have like a 20-story building, 24-story building? Like the
Same
second,
thing.
you would still
The
assume
slab is
or-
the same. The slab has nothing to do with how high it is. Okay, give you an example. Dominic, good question. You walk into a 50-story building, and it's a hotel. The first 6 floors have all kind of crazy configuration. A ballroom here, a bar there. Kid and Wayne is going to spend all his time in the bar. You see? But after getting drunk, they have to crawl up to his room to sleep. Typically, above the 6th floor up, it will be we call typical floor plan. So pretty much every floor is the same setup. Elevator pop up out the way, elevator is in the middle of the building, and then there's a walkway, a corridor to the left and to the right. Both sides are room, right? So it's all like that. So whether that floor is on the 60th floor or on the 25th floor, same setup, same slab.
but your beams change.
Yeah, the beam change. The beam doesn't change that much. The column change.
Yeah, that's
The column and the joint between the beam and the column. Okay. When the building sway, the stiffness of the joint, the column and the beam provide that resistance. But if you have an elevated shaft right in the middle, that absorbs majority of 60-70% of all the lateral load absorbed by the elevator shaft. Okay? So any question with the slab? Any more?
I know when you put stairs in,
Oh.
you put two joists along the stairs, like at the entrance of the stairs going up to your floor, right? How do you cut out your slab and how do you figure out all that stuff? Like all the details about that.
Cut out.
Yeah, so,
You can draw.
yeah. So I was working on it at work like last year, but my boss never explained it to me. Sorry.
Why?
Yeah, right. So let's say your stairs on the side of your building, right? You put two beams over here, back to back, and then you put two beams, like two joists like that for some reason, to reinforce because you're losing support over here because these are your stairs.
Okay. Everybody is trying to explain.
You get what I'm saying?
Okay. Look at the two-story building that I gave you. Okay. This part is a stair. Is that right? Okay. So hypothetically, you probably don't need the width of 30 feet for your stair. Okay. Take a look at all the stair that we have from one floor, from the ground floor to the first floor. Okay. You don't need the 30 feet. So practically, your stair probably. And you walk up, and they probably have a landing here, and then to the upper floor. Okay? So basically, the slab at that level is gone. The only thing in the middle is there's no slab on the top part, there's no slab at the slab at the bottom part is there, but you have this inclined step that go up. Is that right? And then you go to the landing, and from the landing go up again to the upper floor. Okay, okay? Now, before you get up the stair, you're on the slab of the floor. Is that right? Then you walk it up. If you look at the side view, this is what you have, the slab of the floor, which tend to be supported by a beam. Right? They may have the slab all the way underneath the stair. Then you have your stair. That's your landing. Okay? At the end of the landing, there's a beam. Okay? Now you can hypothetically that, hey, I'm not having anyone going under the stair. So I will leave it empty, close it as a dungeon. Okay? So I have my slab that, okay, this is max. Big head, too late. Okay? And Mac is heading up the stair. Okay? His weight and the weight of this land supported here. Okay? Okay. He went up, the other end supported that. All of this, the part that bothers you is this. Rise and run. Is that right? Let's say you just forget about it, cut this out. Now it looks like a consistent thickness of the slab from one beam to the other. Is that right? And there's a middle part that incline. Okay? The load, max weight is still gravity load, dead load, light load comes straight down, no matter where the heat is. Okay? So my question to you, when you guys have question with the stair, you think you can decide a calculate a beam £100, 10 feet? Can you do this?
Impossible.
east, right? Okay? What if I raise the right end up? Muhammad,
Yeah.
you think you can do it?
Yeah. I would just try to support sideways.
Yeah, whatever you want to do. I don't care. But can you find moment and share diagram?
It's possible.
Not possible. You have to be able to do it. Not difficult. Okay. If the load is not perpendicular to the member, okay, bending caused by the perpendicular load. Is that right? So just break it, and the one that parallel to the incline is just shear force, sliding it over. Okay, so only the normal one that causes the bending. Okay, so you can make that adjustment. There's two adjustments. One is, notice the horizontal distance remain the same, but the incline distance is more. Okay, right? So if you treat everything flat, that incline portion will be longer. Is that right? Longer, heavier over that middle part. Or in other words, what I'm saying is that if I have this beam, I'm going to shrink it down to horizontal. Cut it. This top part is only that flat slab, right? But this part is inclined, is that right? So it's longer. Have that put from here with a larger width. Make sense? But it's over the same span. It's still bent over that same span, except that the middle part inclined. So within that projected horizontal distance, you have more material loaded on it. Okay, in terms of dead load. But the life load remains the same because life load is gravity weight, goes straight down, whether it's inclined like that or not. So those steps which consist of the rise and the run, okay, you can treat that as superimposed dead load on top of that middle part and just analyze it. Once you get the moment, the shear, everything go back to the same thing. Yes, Mohammed?
The support that you drew is the same thing as a pin, or would you?
No, it's a beam. Fixed end.
Fix that, okay.
Okay?
So, just curious, when you do the reactions, is it in the center of that?
Or the beam.
Or is it at the end of the beam? Because it looks weird.
It cannot have a center. It's not support.
Yeah.
There are only
Makes
two
sense.
support. You
Oh,
can
I
actually,
see.
you can actually put the beam just at the beginning of the incline and at the end of the incline.
Okay.
You can do that. Some people put it all the way toward the end of the landing. Some people put it at the beginning of the incline, both at the bottom and the top. Nothing wrong with that. The only thing that if you put the beam right at the beginning and the end of the incline, when you walk underneath that, there's a chance that you might hit that beam if you don't have enough clear space. So typically people don't do that. People will put the support beam at the end of the landing, at the bottom, and at the end of the landing on the top, because that tends to hide into the wall, okay, of that space. It's like the bottom is supported there, the top is supported there. So nobody walk under the stair will have a beam right there that will have a chance that you can hit your head. But notice it's a beam, right? Above the support, bottom beam and top beam, negative moment. So your reinforcement will be here, here, on top, and may come down. And in the middle, your positive reinforcement